So I guess we'll get going. So first of all, thanks everybody for coming. This is a thing we do out in Paris now. So Parquet, as many of you know, maybe don't know, is a French headquartered company. We have most of our R&D out there, but we have a big R&D office out here with I think bordering on 100 engineers. And this is a little thing we've gotten going to sort of get a bunch of people together to talk about technology that we're using, that's being used in the community, and a lot of it, of course, is around data, because we're an ad tech company, so we do lots of stuff with data. In our travels, we've met fine folks like Julien here and others, who you will meet today and hear from today. And so, yeah, so the principle of this conference, it's not another big data conference. It sort of grew out of some frustration with some bigger conferences that had a lot of vendor marketing pitches and stuff like that. And we wanted to avoid all of that. We wanted to just have engineers talk to engineers, basically. And so that's the idea. We have a full schedule today. So there's sort of the keynote format in the morning, and then in the afternoon we'll break off into two separate tracks. You'll be hearing from a bunch of folks from Parquet, but you'll also be hearing from a bunch of really, really interesting folks from outside of Parquet as well. And so I hope you enjoy it. And without further ado, I'll hand it off to Julien, and he's going to talk about Parquet and Arrow.
Good morning. Nice to meet you all. And so yeah, I'm going to talk about Arrow and Parquet. And so a little bit about me. So yeah, so I'm currently working at WeWork, and before that I spent 2 years at a startup called Dremio. I'll show you a bit more from it. And before that I was at Twitter, where I co-created Parquet. So back in the day when we had like Hadoop and Vertica. So Vertica is a good columnar parallel database with very low latency. And Hadoop is good at very, very flexible, and you can have a lot of machines, but it's not very efficient. The idea was to bring some of the technologies in Vertica and make Hadoop more of a database and less of a file system. So that's the general idea that kind of started the project. So I got involved in a couple of Apache projects, and I'm going to talk a little bit about the community and how Apache works as well. So first, I'm going to start with more like the community aspect, and then I'll go a little bit in the details of why Columnar and what does it bring, and kind of how Parquet and Arrow can connect and be very useful. And then I'll go more into what the future for Arrow, what the meaning of Arrow in the ecosystem. So the community, right? It's not just, open source is not just about the source. It's not just about publishing the source and you can read it. It's about how do we maintain it together, and how it becomes useful. So really, the way Parquet started, there was a common need for columnar format, right? So there's a lot of, if you look at the database literature in academia, you can see a lot. There's Vertica. There's been a lot of different systems that have been built, and so Vertica was the one we were using at Twitter, and so that kind of been used for the inspiration. But in the Hadoop world, we've been reinventing all the database stuff in a different environment, in a more like deconstructed way. And so there was this need, right? And the technology is known, the principles behind it are known, but there was not a real project that existed. So I started something, and it's based on the Dremel paper. But right from the beginning, I knew I didn't want to do that alone, and I didn't want to have a proprietary format that we would have to integrate with every single thing we would want to use. So really from the beginning, I was prototyping something on the side, and I tried to reach out to other teams to see, hey, can we build this? There's a need for that. Let's do something. So that's where I connected with the Impala team at Cloudera, who was working, developing what is now Apache Impala. And so we started working on it, and shortly after, we met with the Parquet folks who were interested as well in contributing to this. So, I kind of wrote a lot of the Java code on that side. Impala team were interested in all the C++ aspect, and Criteo contributed early on the Hive connectors and all the Hive integration. And so we started from there. And it's important to have a core of different companies that kind of contribute to the same thing and show that it's not owned by one company. We're kind of committed to make that a shared library that everybody can use, and everybody's point of view is going to take that into account. And so, from there, Netflix started contributing to it. Netflix, they decided they were going to use Parquet for their warehouse. And then they decided they were going to use Presto for running it. And so they did all the Presto integration as well. And that, you build a critical mass, and from there it snowballed. And, different teams started using it, and it became the de facto standard, right? So Spark SQL, we didn't even hear from them. They just started using it, and Parquet is a default format for Spark SQL. And, they didn't even ask, they just did it. They didn't ask for help. It's kind of, Apache Drill is also using Parquet's default file format. It's kind of snowballed. And there were a few exceptions, and you know that ORC is like a concurrent similar feature that happened roughly at the same time because there was a need. So naturally there have been different efforts to do the same thing. But I think Parquet has been very popular. The openness of the community was really a key driver of the adoption, I think. And so based on that, so Parquet was a lot of work to kind of build the community and kind of grow this adoption. And for Arrow, which is the same need for in-memory Columnar, and I explain why we didn't just put Parquet in memory. It's kind of the same thing, right? So we're starting from the bottom with the storage layer, and then if you look at the MonetDB paper, which is the first paper is about vectorized execution in memory Columnar. There's a lot of, for a long time, there's a lot of literature about why it's faster to organize around columns in processing because of the properties of the processor. And so, there's this same need for defining this. But now, we're starting from, we already built a community of projects, right? The Spark, SQL, Impala, Criteo, whether it's bigger companies that kind of use those projects and contribute to them, or vendor companies or that build those SQL and Hadoop projects. It's kind of, there's been a lot of connection already around contributing in Parquet, so we can use that and this existing community to kind of build the next things, defining a standard, where the key point is agreeing on the core features of the project, and then start implementing. So I kind of listed. There's probably more project involved, but they're members of all those projects, whether they're Apache or not, mostly Apache project, but not all of them, who contribute to this. And the key point from the beginning, first we agreed on what it was going to do and what the standard would be, and then you need to, once you have that, you can have all the integrations kind of happening in parallel, right? It's kind of, there's no need, open source projects don't really have a roadmap. They have key directions, it makes sense to move them in. And it's kind of different people, we kind of push different aspects of them, right? We don't need to say we do this and then we do that. You just, once you agreed on the core, a lot of different directions can happen in parallel at different speeds, depending on who's motivated, who has time, and who has the capability to do it. So, before, if you look at, and those are kind of a sample of projects that exist, before you would have, there's a lot of complexity in integrating all those projects. So at the bottom, you have a lot of storage layers, whether it's Parquet in files or more service-oriented database like key value stores. You have storage layers, and then you have a lot of different tools to do data analysis or data processing, whether it's more multi-purpose like Spark, where you can do machine learning, you can do SQL, you can do different things. Or Drill, Impala are more specialized in SQL. You can use all those tools. That's some of the great value of the Hadoop ecosystem is you store your data
in a standard representation, it could be Parquet. And then you have a lot of flexibility in using a lot of different tools, right? You can do, plain MapReduce, but you can do SQL, you can do machine learning, and it's very flexible. You can write code and do a lot of things. And the storage layer is about how can I retrieve this data fast so that my processing is efficient and can do things. But the downside of this is increases the complexity, right? So, and as everybody, at the beginning of the Arrow project, it came from the realization that everybody was looking into the next step. How do we do vectorized execution? How do we make things faster? What's the next step? And everybody's starting to implement their own. But now, because they implement their own, it creates a lot of complexity and a lot of waste in performance. Because often to kind of send data from one system to the other, you have to find the lowest common denominator. It's kind of what's easy to pass on is definitely very seldomly the most efficient. So instead of kind of thinking of one-to-one communication and thinking project to project, how do we connect them? If we consider that everybody is looking into columnar in memory, right? And if we can agree on what it's going to look like, then you can remove all the overhead, all the complexity, and just like have a single representation. And once, it reduces the complexity dramatically, and because we agree on what the format is, you remove a lot of cost that is around serialization, deserialization, transforming from one representation to the other. So that's one of the key design consideration for Arrow is looking into serialization-free format. Like the representation in memory is the same as on the wire, so you don't spend a lot of CPU, doing a translation from something. Like if you use regular object-oriented representation in memory of structures and pointers, it's all absolute pointers in memory, which means if you copy them to the wire or to disk, you need to turn it into relative pointers. And then when you put it back in memory, you need to turn it back into absolute pointers. So there's a lot of cost to translate those representations. But if you use a relative pointer representation in memory, then everything's free. So this is a slide. It's self-explanatory why columnar is better than rows. So I'll skip the commentary on that. So really, columnar, it's not complicated. When you think of a table, it's two-dimensional, right? So we have columns, we have rows, but really, when we store it on disk or in memory, it's a linear space, right? We need to turn this two-dimensional thing into a linear space. So there are two main ways you can do that, right? So either you go one row at a time, or you do one column at a time. So the row layout is, the regular, the kind of more natural one. But the downside of it is you keep interleaving values from different types. And often when you query data and you're doing analysis, you're going to look at one column at a time. So you may select A where B equals something. And so you don't need the C's. And this example, I have 3 columns, but really you could have many columns. So if you need 2 values and skip 1 and 2 values and skip 1, it's just really, basically you're scanning everything because the way we access data is not faster to skip values. But if you have a column layout, it's really easy to skip all the values you don't need. So you can scan only the columns that you need to access for your query. And it's a lot faster from I/O perspective because it's really easy to skip entire chunk of the data that you don't need. The other aspect is because we encode together values of the same type, we can do, in a very simple way, we can encode them a lot more efficiently. Right, like for example, if you have strings like variable length values and then integers, let's say for integers, you know the maximum value of the integers, so you can start bit packing them. Let's say the maximum value is 7, well, they fit on 4 bits. So we can pack them on 4 bits at a time. Something we couldn't do if we were putting a string, an int, a string, an int, right? But we can do it because we put all the integers together, so we can pack them more efficiently. and it's also very efficient CPU-wise to decode. And things like dictionary encoding, or various things that can be done more efficiently in that way. So I said earlier, yeah, why didn't we just put Parquet into memory for error? Well, there are different trade-offs, right? So on disk, you're going to store something and you use it in many different queries. So the problem is, how do I retrieve the part of the data I need for that query in memory as fast as possible, right? So that's where the projection and being able to access various columns independently from disk is important. And we want to compress more, because in the traditional spinning disk, the throughput of getting the data off of disk is expensive, so it's worthwhile to compress better and to spend more CPU decoding. And we're mostly going to, stream the data in, so we can make it more compact that way. For the in-memory representation, it's more transient. So we put the data in memory in the context of one query, and and so we're going to lay it out in a certain way for that particular query. So there's less of multiple use case for that one representation. So we can, there's less of the need of doing the projections from different aspects. And the priority is to CPU throughput, because the memory bandwidth is higher than disk bandwidth. So really, we want to reduce the cost of decoding, encoding things. So we want to have the data as close to what is useful to the CPU as possible. And then when you have the data in memory, you also have a bunch of cases when you want random access, when you want to be able to find a value in a row by its index in constant time, which Parquet doesn't provide. You kind of need to scan the values to find a certain offset. When in Arrow, we leave empty slots for null values so that you can find them in constant time. So I'll start with a little bit more details about Parquet, and then I'll go into Arrow. So both Parquet and Arrow support nested data structures, because that's what you find in the real world. It's kind of data processing. It's a compact format, type-aware encodings that I mentioned, better compression. So usually when you convert to Parquet, you get better compression, because just putting data of the same type together makes compression work better. And also we can use encodings that are going to be more efficient, compressing very well compared to general purpose compression like Snappy or Broadly or Z-Standard. But that will compress very well. It was a lot less cost CPU-wise, because you can just know something about the data, right? It's just not random bytes, it's certain values of a certain type. And so it's optimized for I/O, and really one of the goals is to reduce how much data you pull from disk. So whether it's using projections, so reading only the columns that you want, or predicate pushdowns, which is using stats in the data to read only chunks of the data, right? So, and actually, I'll go on. I have a slide with a picture of the format, so it would be easier to explain there. So the nested representation is borrowed from the Dremel paper. And I've shown, my example was a flat table with 3 columns, but we're storing nested data structures. So there's some trick, right, to take those nested data structures and store them in columns. And so the details are from the Dremel paper, and I'm going to skip the details here because it takes a while. But generally, you can think, if you want to store if a value is null, you can use a single bit to say it's defined or it's not defined. So the Dremel model is kind of extended that notion. Then when something is null in your nested data structure, really you say 0 to say if links is null, it's going to be 0, means this branch is not in the document at all. And if forward is null but links is defined, it's going to be 1. And if forward is defined, it's going to be 2. Right, so you extended this notion of, for a flat schema, it's 0 or 1 to define if it's defined or null. And if in a nested one, it's actually the depth at which the null is, right? Because this could be null and this defined, so it's kind of just storing the depth. And for repeated values, like if you have a list, you have a similar mechanism when you have a small number that's going to mark at which level in the tree you start a new list, right? So you're going to, 0 means there's a new record, 1 means there's a new list at the first level, and 2 means there's a new list at the second level. And 3 would mean, well, it's in the same list. It's a new value in the last list. And so, you know, I'm not going to go in the details, and I wrote a blog post to detail and give the example if you want to really understand how that works. But the key thing is you have those 2 small numbers, integers, and you can use trick to encode them very efficiently using bit packing, for example. So you use only a few bits to store them, because you can tell that based on the schema, they're going to be very small numbers because they're bound by the depths of that tree. And so that's the trick to turn nested data structure into a flat representation that can be encoded in a columnar way. And so the key idea of Columnar on disk is, you know, you access only the data you need. With projection push down, you get only the columns you need. With statistics, you can skip a bunch of rows you don't need to scan, and so, you know, minimizing the I/O. And the way a Parquet file looks like, so, you know, there's a footer with metadata like what the schema is and where are the columns in the file. So that's what you use to figure out how to read only the columns I want. If you know what column you want, you read the footer. You have pointers to where the columns are in the files, and you can read only those. And then the file is partitioned in row groups, and really each row group is a columnar. So that's where we represent columns. And then each column is split into pages, and a page is really the unit of compression. So each page is compressed independently. So a page is really the smallest thing you can read at once. And in a page, of course, you have several values, right? You could have 1,000, 10,000, depending on your settings, values in a page. And inside the page, so you have a small header, and then you have the repetition levels and definition levels, which are the small integers that talk about. And then you have the non-null values, right? And you know you can restore what the indices for those values are by looking at the definition levels that tell you when there's a null. When there's a null, we skip the empty slot. And then inside the definition levels, we use, so those are small integers, and we can alternate between run length encoding. Let's say everything is null, then you will have 1,000,000 zeros in there. Then the way you run length encoding encodes it, and you say 1,000,000 0. So you just say there's 1,000,000 0. And if it's alternating null and non-null values, then we use bit packing. You know, it's to store 0 and 1s using 1 bit for each. So in the case of the flat schema, you just have 0 or 1s. And you can encode them very packed using 1 bit at a time. And so depending on what the data looks like, we alternate between one or the other. And you can, you know, if the data changes, it's kind of, you have a block header that tells you what type of encoding is used, and then we have the values. And that's useful because understanding how Parquet is written internally helps us to read it efficiently with arrow. So now I'm going to talk a little bit about arrow and how it works. So similar to Parquet, right, one of the goals is to have a binary definition of the format. Right, the goal is not to say, well, there's some Java implementation you can use, and that's your configuration. The goal is to define very clearly what the binary representation is, and so that, you know, it's language agnostic. You can read it from Java, you can read it from C++, you can share it across processes, and it's going to work, right? You won't have special cases. So that's one key design, is to make it cross-language compatible and really well documented at the binary level. It's not just look at the source code. And it's designed to take advantage of modern CPUs, and I'm going to go over this. It's like, and you can, if you're interested in that topic, go read the MonetDB papers about vectorization, and that's really something that's really interesting on understanding how you can take advantage of how the CPU works to do faster processing. It's embeddable, so usually arrow is an internal representation or can be used for exchange, but it's not really what you use directly, right? It's what's going, all those query engine are going to to use to process data. And so like Parquet, it supports nested data structures and the maximizing CPU throughput by using pipelining, and go over that in my next slide. SIMD instructions or cache locality are the characteristics of the modern CPUs that you want to optimize for. And you can do scatter, gather, I/O. And I'll show you why. But basically, the in-memory representation and the wire representation are the same, which means you don't spend any CPU serializing, deserializing. You can just point at the buffers in memory, pass them to the network stack, and say copy that to the network. And then when reading from the network back to memory, you can use directly whatever buffers you get back from the network stack. You can read directly from that and work directly from that. You don't need to transform it to some other representation. So this slide is about CPU pipelining. So basically, modern CPUs, they don't execute one instruction at a time, right? For various reasons, to make things faster, they start executing, they split the instruction in like 12 steps or something to that order of magnitude. And they start executing the next instruction before the previous one is finished. So here I'm illustrating like an imaginary 4-step pipeline, right? And you can see like instruction A will go over the 4 steps of the pipeline as the time, the ticks from the processor are going. And so ideally, you get them through the pipeline, you get maximum throughput from the processor, but you can tell, very often we have an instruction that depends on the result of the previous one. Like whenever you have an if statement, you're doing a test and you wait for the result of this instruction. And then you're going to decide if we go this way or that way, which means we don't know what the next instruction is going to be until the previous one is finished. All right, so that means, well, you waste all those cycles waiting for the result of the instruction before you start the next one, and that introduces what's called bubbles in the processor. And so you can see, like, every time you have an if statement, and really every virtual function call, because it's like depending on the type of this object, which is data dependent, I'm going to call this code or that code. Every for loop, every if statement, all those things are, every branch is really a data dependent. I'm going to do a test and execute this instruction or this one. So to work around this, the processor has something called a branch prediction. And basically, first thing, instead of waiting to know, I have two options. So I can pick one, start working as if that's the right one and the next one, and worst case, which is what I'm illustrating here, so I'm starting executing B. Worst case, well, B was not the right thing to do, so I cancel everything and I start over. Right? In worst case, it's the same that if I had waited. So I may as well start something because it's not costing me anything more. So of course, the branch prediction is not that smart, right? And one thing you cannot do is go look in the memory of the processor to kind of start guessing what's going to happen. So whenever you have data-dependent branching, it's going to be very bad at predicting what to do next. So the key idea of doing vectorized execution and organizing in column is you can do one way to make the branch prediction very good is just to do the same thing over and over. So if you have a loop and you do the exact same thing in the loop, so every time you start over, you have a branch here, which is, start over. And so 99% of the time, you jump to the same place. So the branch prediction is going to guess right what the next instruction is because it's the first instruction of the loop, right? We keep doing that. And when we exit the loop, then this one time is going to be wrong because the branch prediction is like, oh, for 1,000 times we jumped here, so I'm going to prepare that. And it's going to be wrong, but it's negligible because you're wrong one time out of 1,000 or 10,000. So the key point is you can organize in memory, in column, and be much faster for this. Another aspect is cache locality, because the CPU access to the memory is slow. And so you can be much more efficient at this by avoiding fetching data from memory. Every time the CPU fetches data from memory, it has to wait on it because it takes longer than executing instructions. So same thing creates bubbles. And so to work on this, it has cache on the processor, which is really fast memory that's right in there. So it's going to pull data in there and work on it as much as possible, and then pull more data whenever it doesn't have enough data in there. So because we organize it in columns, and you organize the processing around those columns, you're more precise in the data you fetch. Instead of fetching rows that fetches the values you need, plus a bunch of other columns you may not need, and so you're a lot more efficient in Columnar because you can fetch only the data you need, right? The cache on the processor fetches chunks of memory, right? So you kind of, if you organize all the things you want together, then it's going to be a lot more efficient and need less fetching. So you get better cache locality for this. So that's another aspect of where vectorized help. So here's an illustration of what the arrow representation looks like. So I skipped, of course, for each vector, you have a bit nullability vector that tells you if the value is defined or null. And so I skipped that for brevity, but you can imagine you have bit vectors for all those things too. And so if you have a fixed width value like 18, well, then you can put like just 4 bytes at a time, right? And you know where to find the value. It's just you count the offset, multiply by 4, and you find your value. If you have variable length values like a string, you put them, concatenate them after one another in one vector, and then you have an offset vector that points at the beginning of each value, right? And the way you find the length, and you do the difference between the next value and the previous and the current one, and that gives you the length of the string. 3 minus 0 equals 3. And you always have one more offset just for simplicity, because there's always the offset pointing to the non-existent next value, because that way you can know the length for the last value as well, and it simplifies. And this is composable, right? So when you have lists, like you have a list of variable length values, you have all the values concatenated in one vector, the offset vectors for the values inside the list, and the offset vector for the list itself. So this is the strings, where do each string starts, and this is where each list starts. So the first list has 2 values, so you can see there's going to be 2 values in this list, and 1 value in the second list, right? And then you have the offset of where the values are actually in the last vector. So that's how, and this is all relative, which means I can copy it to disk or copy it to the network and back, and it's the same representation. There's no translation needed. Right, so that's how it's sent on the network. And so I'm going to move a little fast. What time is the next? I think I'm running over a little bit. Apologies to the next speaker. I got 25 minutes? Oh. Yes. I'm good. So I talked about Parquet, I talked about Arrow, and there's some slight differences in those representations. So beside the more, Parquet will do more compression and more encoding, and Arrow will be more the straight representation of values so that we can get maximum CPU out of it. So if you take an example JSON list of values, like very simple. So I'm doing a flat schema on purpose for this example, and extrapolating to nested data structures will be left as an exercise to the reader. I'm happy to talk about it later, but for the purpose of this presentation, I'm just going to do a simple example. So imagine, basically, you have 6 rows, there's 1 column, and it contains a fixed width value, which is a character, and so first 2 are defined, the 3rd row is null, and the 5th row is null as well. So in Parquet, in this case, really the definition level, it's the same as using as a bit to say if it's null or not. So 1 means it's defined, 0 means it's null, and we're going to store all the null values. So when you decode, okay, you can read at this, it's defined, it's A, it's defined, it's B, it's null. I go to the next one, I read C, there's nothing stored for the null values, and that's how you can access data, right? So you kind of expect to read them in order, right? That's how you know which of those values is for which row. In Arrow, to preserve random access in memory and be able to access to a value by its offset, we just have undefined empty slots, right? So here, there's nothing. I mean, it's undefined. There's probably a value there, but you're not supposed to go look at it. And based on the bit vector, you know whether it's defined, you can find a value, or it's null, and you're not going to look at it, but you can find the next offset by its index. So, you know, for the flat case, it's very similar. The main difference between Parquet decoded and Arrow is we don't store the null values. We don't keep empty slot for null values. So when you read from Parquet to Arrow, you know, you can take advantage of that. So the naive version, really, so this is Parquet, this is Arrow. Once you decoded the values, you could just go over all the values. If it's defined, DL standing for definition level, then we set the value, right? Otherwise, we don't set it, right? So we just go over this, and we just read the next value. You know, we keep an iterator on this, so it's kind of stateful. We're going to read through them in order, and you do this. And so the downside is there are a lot of inefficiencies in this. Here we have a big data dependent branch, right? So that means this is a thing that the processor branch prediction algorithm is going to be really bad at predicting what is going to be the right answer. So if like every other value is null, then it's going to be really bad at predicting that, and you get a lot of bubbles. So that's the kind of thing you want to avoid in vectorized execution, because that's what's going to make things much lower than it could be. And also when you set a value in the nullable vector, where you have this abstraction when you have a big vector that stores whether it's defined or not. So you get the right byte that contains a bit you want to set. You use a mask to set that one bit in it that corresponds to this value, and then you set the byte back. So there's lots of operation involved is setting one bit in there. So the naive implementation adds a lot of work here, and it's kind of as a big data dependent branch. So really, you know, file formats are like ogres. They have layers. Anybody has seen Shrek? Just me. Remember that scene? Same. File format are like ogres, and onions, they have layers. And so it's really important to understand those abstraction layers. That's why I was showing this slide with the Parquet format in more details. What are the different layers to kind of do efficient decoding? So remember, for those definition level, actually they're not a list of 1 and 0s, right? So if we iterate on the list of 1 and 0s, we lose a lot of optimization. They are either bit packed, which is what I'm showing in this slide, or run length encoded, which is basically two values, how many of the values and the actual value. So really one trick we can do is first figuring out what's the index of the non-null values if it's bit packed. And really if it's bit packed, you know, the bit vector is going to be exactly the same in both cases, right? So then, you know, the whole ceremony when we were getting the right byte, using a mask to set the bit and setting it back, we can skip all that together because we can just take all the values already bit packed and put them in the other one. So we can very efficiently just get the bits for whether it's null or not. And then really all we need to do is putting the values at the right offset in the target vector. So to do that, we can very efficiently compute all the indices for the values. So here, to do that, you can just convert to a loop, and the key of this is there's no if statement in there anymore. So you can see that for all the values, you may have thousands of values here. We're going to do the same thing in the loop. And you can just, and basically just incrementing, because the index here, the key ID is when it's defined that we need to increment to the next value, and when it's not defined that we don't increment this index, right? So that the key ID here, the current index, we keep adding the definition level here and setting it here, which means we'll just keep setting the value, but whenever we don't increment, we overwrite the previous value. And which means you get the indices, 0, 1, 3, 5 in the target vector, and this one again is setting the value. There's no if statement anymore, right? You take those indices and you set the value. And the key reason we have two for loops here is one is indexed by this size and the other one is indexed by this size. So the trade-off is it's more costly because you need to materialize this in between. But the benefit is there's no if statement in the loops anymore, so they get maximum throughput from the CPU. So if you read that MonetDB paper, a lot of the discussion is about when this trade-off is useful, because there will be cases when it's more costly to materialize intermediary stuff for the benefits of getting full throughput from the processor. So the paper discusses like trade-off in which cases it's useful or not. And there's also, it's a lot about how you combine those loops, right? So you want to minimize how much stuff you materialize in between. And so, when things are over the same array, you can combine them in one loop. So I'm not going to go into that because it's fairly complicated and it takes a long time to explain, but you can read that paper and it's very interesting. So here, key thing is there's no branching, so we get maximum throughput. And in the run length encoding case, which really is you're going to have big batches where everything is defined or everything is null, you can take advantage of that because now there's no decoding involved anymore. You can say, hey, so I have a first range of 4 values that are defined and a second range of 2 values that are not defined. And that's for the sake of this example so that it fits on the slide, but really you would have 5,000 defined values and maybe 2,000 non-defined values. And if you sort your data set, for example, this is going to be can happen, right? In a lot of cases, everything's defined, even if, or it's mostly defined, even if it accepts null, or sometimes everything is not defined because it's very sparse data set. So in that case, the interesting part is the if statement goes around the loop, right? So instead of having a loop and putting the if statement in the middle, you put the if statement around and you say, hey, look, I have 5,000 defined values, what do I do? And in that case, the bit vector, you can set a range. So very efficiently, setting 8 bits to 1 in a byte is very efficient. You just write 255, right? You've set all the bits at once. And, in the case where it's null, where there's nothing to do. You do nothing for the null values. And for the defined values, well, you just write the values next to each other, right? You just copy this into that. And this becomes really, really efficient, right? There's almost no decoding anymore. So if you don't look inside the abstraction layer and you just iterate on the one, you have a big if statement and you do a lot of inefficient things. But if you look at what the actual format is and peel away the abstraction layers, then you can be very efficient at just copying the data over. And it happens quite often, right? So it's good to have a format that can support null values, but in a lot of cases it will be all defined or mostly null, it happens to. And so it's important to be able to fall back to the very efficient case. Well, nobody told me it was all defined, but we can take advantage of that the data is actually all defined. Right, so here's the value. So the other things we can look into is predicate push down. So same ID, and I apologize, I'm going to go a little bit fast on this one, but so it's applying the same principle to using filters. The part I said, like so we can read only the columns we want, but we can also skip the values we don't want. So we can take advantage of the fact that we have statistics for each row group, so you can skip entire row group. If you're looking for E equals 3, but the minimum for this row group is 5, it's never going to be into it. So you can skip that. And then you have statistics for each page as well, so you can have finer granularity skipping there as well. So naive implementation is you take your data, you decode it, and then you apply the filter and you keep only the values that match the filter. That's a naive implementation. It works. That's based on the abstraction layer. You can do that. But if you look at what the format is actually, so first, you can skip the row groups altogether. So I'm not even showing that. But first, you can look at the stats in the page header. You skip the pages you don't need to read because you're not going to find the value into it. You decode only the pages you need to decode. Then you apply the filter on those pages, right? And then you get the delta. So in this case, we chose to represent the result of the filter by how many values you skip, right? So in the previous example, so for this value, we keep the first value. So delta is 0, and then we skip one value, so delta is 1, and that's the last value we keep, so we don't need to keep any one of those. So the delta vectors is telling you to find the other values in the other columns, how many values you need to skip. So the idea is first, you fetch only the column you filter on. And you can skip reading the pages you don't need, so there's no I/O here. Based on stat, you skip some pages so you don't read them from disk. And then decoding, since you don't read them from disk, you don't need to decode them either. No decompression. So you save I/O, you save CPU. And then you evaluate the deltas, and now you can also use the header metadata on the other columns, the columns you're projecting, to skip a bunch of pages, right? Because we're taking only the first row and the third row, we're probably going to skip a lot of pages. We don't need to read those pages, these one and those ones, because we're going to read only some of it, right? So each page header tells you how many values you have in it, so you know that you can skip a page because you don't need to read that. So again, we save in I/O. We don't need to read them from disk. We don't need to decompress them. We don't need to decode them. And so, by decomposing the step, you can save time because I/O is expensive, CPU decoding is expensive, so peeling away the abstraction layers enables you to much more efficient decoding. So now I'm going to talk about the application of Arrow. So I talked about the in-memory representation. And so the key is, because you use columnar representation and you organize your processing around those columns doing vectorized execution, you can get better speed from your CPU thanks to pipelining and cache locality. And so modern query processors use those approaches to go faster. But then, in the distributed world, you exchange this data from machine to machine. So the whole serialization, zero cost serialization, deserialization is very important. And so that's the second aspect. And the third aspect is because we talk to each other as open source projects and making it standard and say, look, we want to use the same in-memory representation instead of each having our own, then you also don't pay any cost in conversion from one system to the other. It makes it really easy to interact. So we are at this phase where all those projects agreed on the format, and then it started being integrated in various projects, like PySpark is using it, for example. Here's an example. And each project, we want to drive adoption in every project, and we are at that phase. So here's an example. Let's say you have a SQL engine, and could be in Java, could be in C++. You can think either Apache Drill, Spark SQL, Impala. And you can have a separate Python process, and you can write your user-defined function in Python. So it's very common use case. Typically, the PySpark is people writing Python code and running into Spark. So originally, the way it worked is what's using Pickle, which is a serialization mechanism for serializing Python object. And that created a lot of overhead in serializing, deserializing those objects because you do a lot of tiny allocations, a lot of pointer lookup, and it's very slow from a data processing perspective. So instead, if you can work directly on top of Arrow, you can use Arrow for communication And assuming, so right now we are kind of in the early phase, so the communication for sending arrow across the wire has been implemented, but it's not fully integrated yet. But in the future, the key idea is you use a columnar representation in memory in your SQL engine to do go fast. And you can have an operator that produces some data in memory in columnar format. You can use shared memory to give a pointer to it to the user-defined function, and really those are all immutable, right? They're generated, and once they're generated, you don't touch them. So it's kind of easy to share them because there's not going to be any concurrent modification to them. So you can give it in read-only to a user-defined function that stays in a separate process, and that's good because usually you don't want to mix user code with platform code in the same process. So this changes more and is less vetted than this. So if it crashes, it should not impact the other queries running on it. And there's better isolation, resource isolation, and resource management this way. And then it produces the output of the functions and then sends it back in read-only. And so you remove entirely the cost of serialization, deserialization. Even buffer copy is removed if you run on the same process and use shared memory. And the SQL engine is that much faster because it can work in a vectorized way instead of the old row-oriented execution. And another aspect is because we make this standard, now your Python UDF library becomes standard. I don't know if you've ever tried to use your user-defined function in Hive versus Spark SQL versus Impala versus other things, but it doesn't work that way, right? You need to re-implement the UDFs every time, and they may be in a different language, and they may be running in the same process and all of that. Now you just define the universal UDF API. As long as you can speak arrow, those work in any context. So that's another perspective. Another way, is to exchange data, right? So you can arrow RPC, kind of REST-ish. You can retrieve data in arrow format, serve data in arrow format, simplify integration across system. And you can really have this arrow-based pipe when you can send record batches, which is like a subset of rows in columnar format, and stream them and do exchanges. And I'll give a few examples. So you can imagine a storage layer like Kudu, for example, and I speak a little bit about Kudu. And typically, when you have the storage layer, from the query perspective, the optimizer will try to do push downs, right? It's going to try to figure out what filters, what projection you're applying on this storage layer, and push it down all the way so that we can reduce the I/O to the minimum, right? Push this information down to the storage layer so you can skip I/O and skip decoding a bunch of stuff. And then once you've done that, you can produce data, and you want it to be ready for processing. Right, so historically, Kudu is a columnar storage layer, and it knows how to do push downs, projection push down, filter push down. But I'll take the example of Apache Drill that I know a little bit better. And Apache Drill uses arrow columnar representation in memory, and so it's columnar in memory, it's columnar on disk, except for historical reason, Kudu takes its columnar data, does the push down, and then materialize row-oriented buffers. Because a lot of the existing system consume rows, right? So it returns row-oriented buffers. So it does the work of converting columns into rows. And then the first thing Drill does, it takes those row buffers and convert them back into columns in memory. So you can see how there's a lot of inefficiencies here. And so ideally, and so that's kind of like the future, we can convert the columnar representation into a columnar memory buffers, like doing the decoding, so removing all the abstraction of what's specific to Kudu and how they store stuff. And send the data in arrow format, and because it's the internal representation for SQL execution, there's no transformation involved, right? You can remove all the cost of transforming from one to the other and be very efficient. And also, because we're turning column to column, you can do that in a vectorized way. You can decode one column at a time and be very efficient, take advantage of all those CPU specific things of pipelining and cache locality to make this really fast. So that's another example of doing a similar thing. You can use an arrow-based cache in memory. It's like some of the things the database do is kind of keeping hot data in memory for faster access. So you could use Arrow as a shared cache pools, right? One of the key things that's happening in the Hadoop ecosystem is with deconstructing the database, right? You have different storage layers, whether it's Parquet with immutable data, Kudu, HBase, Cassandra are mutable data structures. And you have Calcite, which is the optimizer of the database. And you have various query engine, whether it's Impala or Drill or Spark SQL, or apologies for the ones I'm forgetting. And you have all those things that starts working together, and you can use machine learning, and we kind of making it all much more flexible. But we need a few standards in between so that it stays efficient. And so there's an example of how a simple query execution works, like in a simple system. So if you do a simple aggregation, like select sum A from T group by B, the first thing it's going to be doing is read the data, right? So let's say you have Parquet files, and so you'll have scanners. So I'm assuming 3 machines in your cluster for this slide. And so each machine will read, each thread will read a subset in parallel. And then it's going to do partial aggregation locally, grouping by key. But it's going to prepare one for each other node in the cluster. So here, right, the main goal is to put everything for the same key and send it to the same machine. So you prepare this data, right? You have these 3 areas you keep summing in. And whenever it's full, you send it to the other machine, right? So those are Arrow record batches that we call subset of the data, and you send them to the right machine. And so you write it directly in the right place, and then you send it over the network. There's no serialization involved, no cost of serialization. And then the partial aggregation is just you add the partial sums together in one final result and send that to the user. So it's kind of an example of what the query physical plan looks like for a simple query. And now Arrow is used for it. So there's been a lot of work involved in PySpark, and thanks to Wes McKinney and Lee from his team at 2 Sigma, I've been doing a lot of work on that, and some IBM folks as well. So Wes McKinney is the Pandas guy, which is a very popular Python toolkit for doing data analysis, and they get very good results. Wes has been involved in all the C++ libraries for Parquet and Arrow, and a very good result in improving the integrations. Language binding, so both Arrow and Java and Parquet have Java, C++, Python, Pandas integration. Arrow has some other bindings as well that have been done. Once you have the C++ implementation, you can do a lot of bindings on top of it. Engine integration in Parquet, I'm not stop listing them because it's most of them. I actually wouldn't be able to name exceptions. But an Arrow, it's work in progress, so Drill, Pandas are Spark. Actually, the first version are in there already, and so speeding up PySpark quite a bit by using Arrow for communication instead of pickle-based serialization, deserialization. So I need to update that because there have been more releases since then. But it's kind of showing that there have been initial releases with how many changes in the release, how many days since the previous release. So the goal is to get them, number of days is going down, kind of having very frequent release, like monthly or so. And it's and there's still a lot of stuff happening. There's been some finalizing all the more exotic types and stuff like that. So if you're interested, you can start looking at some of the stuff that's happening. We've been improving the Parquet statistic storage to make it even easier to skip pages in Parquet, the stuff I was talking about. There's some discussion on how to standardize an Arrow REST API to make it really dead simple to integrate things. And some other bindings are in the work for Arrow. If you want to get involved, this is all Apache projects, right? Everybody's welcome. Just be nice, right? This is not the Linux kernel development thing. Everybody's nice. you know, there's no Linus in Parquet and Arrow. So there are some Slack channels. You can join to chat. You can follow the Twitter account. We try to post like new stuff that's happening, even people contributing pull requests and stuff. There's file format. The dev list is always the starting point. You can dev-subscribe to join the mailing list and do that. And this is the vendor part and non-vendor part. Sorry. This talk is sponsored by WeWork. We're building an awesome data engineering team in San Francisco. If you're interested in that, or in New York as well. But I'm based in San Francisco, and we're building a team here as well. Come talk to me or Yang, sitting in the back here. And we can give you information about that. Thank you for your time. I hope I didn't sleep too much.